different neat examples of things that you can do with them. A differential equation relates a function to that function's derivative. So we have already technically seen some differential equations. So, for example, dy over dx equals 3x plus 2 is a differential equation. Second derivative, written this way, this is a differential equation. Now, we have only been looking at differential equations where we just took the derivative of y and we called it dy dx. Technically, that's writing that as a differential equation. What we'll look at in this unit is what does it look like when that is more complicated than just taking a straight derivative for that. So a phrase that we have to know about is directly proportional. I think this is technically maybe in Math 1 some. I do not do much with this. If two quantities A and B are directly proportional, then A equals K times B, where K is a constant. Direct proportionality is a really simple idea. It doesn't necessarily seem like that in the definition, but if two things are directly proportional, then to get one of your values, you just have to multiply the other by a number, a constant number. For example, one of the best examples of direct proportionality that you can relate to is hourly salaries, or not salary, hourly wages, right? So your wages that you are paid are directly proportional to the number of hours you work. And in that case, your constant of proportionality, that K, would be how much you get paid per hour, right? So if you want to know how much you make, then you just need to take how much you make per hour, your constant of proportionality, multiply it by the number of hours you work, you get how much money you make. Unless, if the stupid government wouldn't take half of it and complicate things. But at least your gross pay, right? Somehow, I should know that better than I do. Let's look in this section in 7.1. We're not actually solving any differential equations. We're almost like translating. So we are writing things here. So we're taking the words that they give us and writing it as a differential equation. We will not be solving them at this point or doing anything further than that. So the rate at which a quantity M of a certain radioactive substance decays is proportional to the amount of substance present at a given time. Which of the following differential equations that could describe the relationship? So, let's see. If everybody will, let's close those computers. I feel like they are a distraction to us. So let's put those down. You won't need them on this section at all. So, in this case, when we see the rate at which quantity M decays, the rate that something is changing, we've already talked about this a lot when we did like related rate stuff, right? That's going to be dm dt. So we got dm dt. And so this rate at which the quantity M of a certain radioactive substance decays is proportional to, when you see is, you're going to write an equal sign. And when you see that something is proportional to, that means some constant times that times another value is going to give you that expression. So a lot of times I use a K right here, but K is just any constant. You'll see in our answer choices they don't put a K here. And then the last part, so it's proportional to the, another color, the amount of substance present. So in this case, the amount of the substance present, what is that represented by? It is M in this case, because it tells you M it's talking about the rate right here, so that's dm dt, but m is a certain radioactive substance, right? So m itself tells you how much of it you have. So this right here, the amount present, that's your m for that. That equal sign should be green right there. So we are looking for an answer choice that is of this format. Okay? Now, there's two answer choices that kind of look like they could be the answer. Which ones are those? B and D. Which one do you guys think it's going to be? It's going to be B. Why are you choosing B instead of choosing D? Okay, because we are looking at decay. So you're going to have a negative constant of proportionality because it's going to decrease there. So the correct answer for this one is B. Okay, we're going to learn more about what to do with that later in this unit. But right now, we're just kind of translating the situation to what the equation would look like. So here is a very long one. Okay, the population of a certain species of insect is given by a differentiable function p, where p of t is the number of insects in the population in millions at time t, where t is measured in days. When the environmental conditions are right, the population increases with respect to time at a rate that is directly proportional to the population. Starting August 15th, the conditions were favorable and the population began increasing. On August 20th, 5 days later, there were an estimated 10 million insects, and the population was increasing at a rate of 2 million insects per day. Which of the following is a differential equation that models the situation? Now, this one's going to have a little bit more work to go with it. We're going to actually find the K for this. But we're going to start by writing our differential equation like we did before. So the beginning part is just basically telling you P is population. Right? It says when the environmental conditions are right, the population increases with respect to time at a rate. So population increases with respect to time at a rate. What's that telling us to do? That is dp dt. So dp dt. And we know that it is the dp dt and not just p because it's a rate there. And we see is, what do we write for is? That's our equal sign. We see directly proportional to, what do we write for that? K. That's our constant of proportionality right there. And it's directly proportional to the population. What do we write for that? That is P. Okay? So we probably could go ahead and rule out A as an answer choice because it has nothing to do with dp dt. But then we've got three answers that could all possibly be the correct answer. This one is actually asking us to find the K value here. So let's.
Could you rule out B because it's just got the T next to it?
Oh yes, you were right about that. We could rule out B because of the T that is included there. In this case, because it is a differential equation and not an exponential equation, 1/5 could still be an increase for that. So you're really actually going to see negative K's whenever you have something that's decreasing for differential equations. So it still could possibly be C for that. So, so it tells us starting August 15th, conditions were favorable. Population began increasing. On August 20th, 5 days later, there were an estimated 10 million insects, and the population was increasing at a rate of 2 million insects per day. They give you too much information here trying to confuse you, okay? Because this is a very simple equation that only has 3 variables. You do not want to replace K because that's what we're looking for. So they've given you more information than you really need. What is dp dt? it's going to be 2 million insects per day, right? Because the population was increasing at a rate of 2 million insects per day. So the dp/dt is 2. We're going to keep the k. What's the population? It is 10 there. So if we solve for k, we just have to divide by 10. And so we do get 1/5 for this one. Oh, let's see. Somebody will go get Lucas. Tell him his time is up. He's in Miss Swisher's room. And so we get C for our answer choice there. Okay. Questions there? You just have to be very patient with all that reading. It gets super confusing in Seaman because there's so many words right there. Might be time for some of Miss Reed's and Miss Soare's top students to shine on these particular ones. For 3, a scientist is studying the relationship of two quantities, S and T, in an experiment. The scientist finds that under certain conditions, as the quantity of S increases, the quantity of T decreases. After taking measurements, the scientist determines that the rate of change of the quantity of S with respect to the quantity of T is inversely proportional to the natural logarithm of the quantity of T. Which of the following is a differential equation that could describe the relationship? So we see a different phrase right here. We see inversely proportional. So for an inversely proportional relationship, I probably should have put it in the notes and I didn't. Inversely, or let's see, if A, right this way, if A is inversely proportional to B, that would imply that A equals K divided by B. Thank you. Okay, we're right there. So the way we set this one up is going to be a little bit different. But as far as reading through, it's going to still sort of read the same. So tell us about S and T. And really, all that first stuff is beginning information. The scientist determines that the rate of change of the quantity S, what is that? That is ds dt. Make sure whenever you do this, like if this were free response, if they use a capital S, you need to use a capital S. If they use a lowercase h, you need to use a lowercase h. It makes a difference in this. With respect, oh wait, hold on. I've messed up. It is the rate of change of the quantity S with respect to the quantity of T. What's wrong about what I just wrote? I need the capital T. There, I've proven my point on this. So it's ds d capital T. Related rates, it was almost always time, right? It was dx, dt, dy, dt, it can be another variable for that. So we got ds dt. Is, what do we write for is? Equals. Inversely proportional. Inversely proportional is not going to be k times a quantity, but it's going to be k divided by a quantity. Okay? And then we have the natural logarithm of the quantity t. So that is ln t. And if we look at our answer choices, hopefully it's there. It is C for that. Okay. Questions? Okay, try 4 on your own. The jogger's acceleration here, so acceleration is going to be the second derivative of position. So since P is position, that is d squared P over dt squared. And is, of course, is your equal sign. And then proportional to, that's where we put our K. And then we have the square root of the time since the start of the run. So square root of t for that. So C is the correct answer for that one. Okay, questions there? All right. Try this one. It's a lot like number 2. Questions there? Okay. Last one. Pressure applied to a gas is increased while the gas is held at a constant temperature. Then the volume of the gas will decrease. The rate of change of the volume of gas with respect to the pressure is proportional to the reciprocal of the square of the pressure. Which of the following is a differential equation that could describe this relationship? So the first part's really just defining what you've got. Rate of change of the volume, what's that? dV dt. Oh, yeah. This is a bad habit that I need to get out of. I want to put dV dt because I want any rate to always be dt. Because it's pretty much always been on a related rate stuff, but it's not. With respect to the pressure, so what should be on the bottom, dP, right there, is your equal sign directly, or they don't say directly proportional, they just say proportional, but if they say proportional without the directly, they still are talking about directly proportional. Probably. Because when we say the reciprocal, that's like 1 over whatever. That flips the fraction, right? And to do that, we do 1 over whatever we're talking about next. So you're probably right about that, Xander. They could have called this inversely proportional to the square of the pressure, but they didn't use that language. Yeah. Inversely proportional, I think, would be a little easier to look at there. And then the square of the pressure is P squared for that. And then, of course, that K would be like K over 1. So we could write this as dV dP equals K over P squared. And that one is... Yes, C. I was having a hard time seeing the difference between C and D, but we have dP over dV right here, which is not correct. Correct. Okay, so that's really yes. So they tell us that our domain for F is 0 to 5. Then they ask us about the domain for H here. So what we want to think about in this case is if we're plugging in these values, what like the X values would happen, what would happen to those X values. So for this case, whenever I am integrating, I'm going from 0 to X over 2 plus 3. So this function right here is only defined from 0 to 5. So I can only use h if f is defined there. But it's not as simple as just doing from 0 to 5 again, because my integral goes from 0 to x over 2 plus 3. All right. So for this function, first of all, for a graph, what does it mean to find, like, for example, if I want the integral from 0 to 2 of f of t dt? What does that mean? So that is area between the curve and the x-axis from 0 to 2, right? Like it would be talking about, if I'm integrating from 0 to 2, this right here is talking about this area underneath the curve. That's another thing, like on that last free response question, we were having trouble with that. The first part of that last free response question on the test, we did not do well on. So if I am looking at this, if I want to integrate, I can integrate from 0 to 0, and I could integrate from 0 to 5, but I can't integrate outside of that, right? Because f doesn't exist outside of that. So for this, that top limit right there, the lowest it could be is 0, the highest it could be is 5. But that does not mean the x value is 0 or 5, right? So what I'm going to do for part A is I'm going to say x over 2 plus 3 equals 0. I'm thinking about what number do I need to plug in that would give me 0, right? So I would subtract that 3. So x over 2 would equal -3, and I'd have to multiply by 2. So x would equal -6. So I can evaluate h all the way down to -6, because when I plug in -6, I get 0, and I could integrate this from 0 to 0. Okay? And then the highest number that x over 2 plus 3 could be is 5, right? Because outside of 5, f does not exist. So I would do x over 2 plus 3 equals 5. And I would need to subtract 3 from both sides. X over 2 would equal 2. I would multiply both sides by 2, and x would equal 4. So our domain of h is from -6 to +4. Okay, questions? Okay. The second piece asks us for h prime of 2. Okay, so if the function they've given me right there, the integral function is h. If I want h prime of 2, h prime of x is the derivative of the integral from 0 to x over 2 plus 3 f of t dt. And what happens when I take the derivative of an integral? Okay, plug the top stuff in for your t. The derivative and the integral cancel each other out, so we would just have f of x over 2 plus 3. And then we've got to multiply by the derivative of x over 2 plus 3. What would the derivative of x over 2 plus 3 be? It's 1/2. Because x over 2 is the same as 1/2 times x. So its derivative is just 1/2. Okay, you might want to rewrite this with h prime, this is part B, of x equals 1/2 times f of x over 2 plus 3. That's not necessary, but you might want to just clean it up a little bit. Now, that's our function for our derivative. They asked us to evaluate this at 2, so h prime of 2 is going to be 1/2 f of 2 over 2 plus 3. And 2 over 2 plus 3 is 1 plus 3, which is 4. So we got 1/2 f of 4. How do we find f of 4? Chart. So we look, yeah, if we go up here to the graph, what is f of 4? It is -3. It's just the value of that point, right? Because this is the graph of f. So we get -4. So 1/2 times -4, which will give us -2. Oh, I'm sorry. So -3, which will give us -3/2, or -1.5. Okay. C asks us where h has a minimum, and we have to show the analysis that leads to our conclusion. Okay. This is going to be tricky for this. So first of all, if we're looking for a minimum, and this one does not say relative minimum. If it does not say relative, it means absolute. And this is on a closed interval. So I think on the test, on that second FRQ, we all did pretty badly on, well, actually, most of you got 2 out of the 3 points. So I'm not saying pretty badly, but I don't think anybody got the absolute minimum for that. Because for absolute minimum, that's the lowest point on the whole graph, and it can be the endpoints of the graph. And on that problem, it was the endpoint of the graph, and nobody really checked for the endpoints of the graph. I think it was on that third question there. Because what we could have happening here is we could have a relative maximum or a relative minimum, but the absolute is actually on the edges here. So we have to check for that. So when we're talking about minimums, we're thinking about the derivative, and we're thinking about the derivative switching from positive to negative, or negative to actually a minimum is going to be negative to positive. But it could also be the endpoints for that as well. So in this case, we want to know our derivative, h prime of x, is 1/2 f of x over 2 plus 3. We want to know where this equals 0. But this is tricky because it's not just f of x. Like, we can't just look at the graph, right? Because the derivative is not just the graph. It's 1/2 f of x plus 3. Now, does the 1/2 really affect anything? It does not. 1/2 does not really affect anything because I could divide both sides by 1/2. And now I'm looking for where f of x over 2 plus 3 equals 0. Now, I could go look at where my f equals 0, right? But I just got to keep in mind that's not going to be the x coordinate. So where does f equal 0? At 2, right? So I know that f of 2 equals 0, right? So what equation could I set up that'll give me the x value where this derivative equals 0? Okay, we're looking for this inside part right here to match the inside part right here. So we can say x over 2 plus 3 equals 2. And we will subtract 3. So x over 2 equals negative 1. And we will multiply by 2. And so x will equal negative 2. This is not necessarily the answer. This is a critical point here. So we would need to make ourselves, well, let's think about it. How do I want to think about this? I'm going to run out of time is what's going to happen. Let's make a sign line, but then we're going to stop because we're going to be out of time. So a sign line here, I would start at negative 6 because that was our lowest domain point. I'm going to put negative 2 here in the middle because it's our critical point. I'm going to put, what was it, 4 as our upper limit. And we're thinking about h prime of x. So let's think about plugging a number into our derivative. So for our, like, an easy, you pick let's just pick negative 4 because it's right there in the middle for this one. So if I'm doing h prime of negative 4, I'm going to have 1/2 times f of negative 4 divided by 2 plus 3. Which would be 1/2 f of, it's going to be negative 2 plus 3, which will be 1. How do I find f of 1? Graph. The graph up here, f of 1 is 2. So I would get 1/2 times 2, which gives me 1. That's a positive number. So that section is positive. And then I want to do the same thing with a number over here. I like 0 for that. So h prime of 0 would be 1/2 f of 0 over 2 plus 3, which is going to be 1/2 f of 3. And f of 3, I'm just finding from my graph here, it is at negative 2. So I got 1/2 of negative 2, negative 1. And that gives me a negative right here. And so we need to do a little bit more to finish this that I will finish up for you guys at the beginning of class tomorrow. But that gets us